Hello. In this video, we are going to talk about directional derivatives and the gradient vector. First, I would like to start with the gradient vector. It's a vector which we will see in many contexts. So, the gradient of an n variable function, where the variables are x1, x2 to xn, at the point P, whose components are a1, a2 to an, is vector delta fp, whose components are partial derivative of f with respect to x1 evaluated at the point P, partial derivative of f at x2 evaluated at point P, and we continue until we evaluate all partial derivatives of f at the point P. So, since we are in this course are interested mostly with 2 and 3 variable functions, I'm going to give in details the definition of the gradient of 2 and 3 variable functions. So, if f is a 2 variable function whose variables are x and y, then the gradient of f at the point P, whose components are x0, y0, is the vector whose components are partial derivative of f with respect to x evaluated at x0, y0, and partial derivative of f with respect to y evaluated at where the variables are x, y, and z, then the gradient of f has now 3 components. Partial derivative of f with respect to x at the point, partial derivative of f with respect to y evaluated at the point, and partial derivative of f with respect to z evaluated at the point. Okay, so now let's see an example. Here we have a 2 variable function. Now we'd like to find the gradient of this function at the point 2, negative 2. So we first need the partial derivatives. So I'm going to apply the chain rule. So tangent inverse, the derivative is 1 over 1 plus x over y squared times the derivative of the inner function with respect to x, which will give us 1 over y, and I will need to evaluate this partial derivative at the point 2, negative 2. So x over y will be negative 1, its square will be 1, so we are going to have 1 over 2 times 1 over y, which is 1 over negative 2. So the value of the partial derivative of f with respect to x at the point 2, negative 2 is negative 1 over 4. Now let's do it for the partial derivative with respect to y. So the derivative of the tangent inverse times the derivative of the inner function with respect to y, which will give us negative x over y squared. And then we evaluate this at the point. So we get 1 over 2 from the first part of the derivative, and then negative 2 over 4, which simplifies to, again, negative 1 over 4. So, the gradient vector of f at the point 2, negative 2 is the vector whose components are negative 1 over 4 and negative 1 over 4. Okay, now let's look at some properties of the gradient vector. The gradient of f plus g is equal to the gradient of f plus gradient of g. gradient of f minus g is gradient of f minus gradient of g. The gradient of k times f is k times the gradient of f, where k is a constant. The gradient of f times g is g times gradient of f plus f times the gradient of g. And lastly, the gradient of f over g is equal to g times gradient of f minus f times the gradient of g all over g squared. Now, I would like you to note that these properties are same as derivation properties. Now, let's talk about directional derivatives. I'm going to start with the directional derivative of a two-variable function. So, let f be our two-variable function, where x and y are the variables. Its directional derivative at the point x0, y0 in the direction of the unit vector u, whose components are a and b, is the following limit. Limit as h goes to 0 of f of x0 plus ah, y0 plus bh, minus f of x0, y0 all over h. Now, the notation we use for this limit is d subscript the unit vector u of f evaluated at the point x0, y0. Now, I would like to remark the following. We have already seen the partial derivatives of a two-variable function with respect to variables x and y. Their limit definition is at the point x0, y0 is the following limit: f of x0 plus h, y0 minus f of x0, y0 all over h. Now, if I compare this limit with the following limit, I observe that this partial derivative with respect to x is in fact the directional derivative of f in the direction of the unit vector I, whose components are 1 and 0. Now, similarly, for the partial derivative of f with respect to y, if I compare its limit definition with the limit definition of the directional derivative, then I observe that the partial derivative with respect to y is in fact directional derivative of f in the direction of the unit vector j, whose components are 0 and 1. Now, let me give an interpretation of the directional derivative. So, here we have a two-variable function. This blue surface is the graph of this two-variable function, and I mark my point P0 on this surface. Then in green, I consider a plane Q, which is through this point P0, and which also contains the directional unit vector u. Now, this plane intersects the surface S in the black curve C. Then I consider the tangent line to this black curve C at the point P0. Then the slope of the tangent line to this curve C at the point P0, which is the rate of change of f in direction of u, is the directional derivative of f in direction of u. So, the directional derivative of f in direction of u is in fact the rate of change of f in direction of u. Now, let's talk about a theorem which will tell us when f has directional derivative and how to calculate the directional derivative in terms of the gradient vector. Now, if f is differentiable at the point x0, y0, then f has a directional derivative at that point in the direction of any unit vector AB, and we calculate this directional derivative using the following formula. the partial derivative of f with respect to x evaluated at x naught y naught times a plus partial derivative of f with respect to y evaluated at the point times b. Now, this formula can be also rewritten as follows. I recognize the sum as the dot product of the gradient vector and the unit vector u. Now, we can rewrite the dot product using the angle between the vectors. So it is the magnitude of the gradient vector times the magnitude of the vector u, which is 1 since it is the unit vector, times cosine theta, where theta is the angle between these two vectors. Now, to evaluate the directional derivative, you can use any of these formulas. So, let's see an application. We'd like to find the directional derivative of this two-variable function, 2xy plus y cubed, at the point negative 2, 1 in the direction of the vector 2, negative 3. So, I am first going to calculate the gradient vector of f. So for that, we will need the partial derivatives. With respect to x, we have 2y. Then I evaluate this at the point negative 2, 1. And we get 2. The partial derivative with respect to y is 2x plus 3y squared, evaluated at the point, and we get negative 4 plus 3, which gives us negative 1. So, the gradient vector of f at the point negative 2, 1 is 2, negative 1. Okay, next let's look at our vector. Now, the vector 2, negative 3 is not a unit vector because its magnitude is, as you see, 4 plus 9, which is root 30. So I need to calculate the directional derivative, I need to find a unit vector in the direction of the vector given in the question. So the way to obtain such a vector is to divide the given vector by its magnitude. So this vector is a unit vector in the direction of the vector 2, negative 3 given in the question. So using this unit vector and the gradient vector, we can calculate our directional derivative at the point negative 2, 1. So from the formula, this is the gradient vector at the point negative 2, 1, dot product the unit vector. So gradient vector has components 2, -1. The unit vector is 1 over root 13, 2, -3. So I will write the scalar in the front. And then we have 2 times 2, which is 4, plus -1 times -3, which is 3. So the directional derivative of f at the point -2, 1 in direction of the unit vector u is 7 over root 13. We are going to finish this video with some properties of directional derivatives. So let's consider either a 2 or 3 variable function. Now we have seen that the directional derivative of f in the direction of the unit vector u at point P is the gradient of f dot product with the direction vector. And using the angle between these 2 vectors, I can express the directional derivative as the gradient of the magnitude of the gradient vector times the cosine of the angle. Now, using this expression of the directional derivative, we can derive some conclusions. First of all, the maximum value of the directional derivative occurs when the gradient vector and the direction vector have the same direction, which means when the angle between these 2 vectors is equal to 0, because at this angle the cosine is going to reach its maximum value. And in this case, the maximum value of the directional derivative is going to be the magnitude of the gradient vector. So as I said, the cosine will be 1 and the directional derivative will be equal to the magnitude of the gradient. And the direction vector is going to be the unit vector in the direction of the gradient vector. The second conclusion that we can draw from this formula is about the minimum value of the directional derivative. So the minimum value of the directional derivative of f occurs when the gradient vector and the direction vector u are in opposite direction, which means that the angle between them is equal to pi. So again, if we go back to the formula and put pi for theta, the directional derivative, it's going to get its minimum value because cosine will get its minimum value, which is -1. Now, in that case, the minimum value of the directional derivative is going to be negative magnitude of the gradient vector, and the direction vector, it's going to be the unit vector in the opposite direction. This minus will tell you that this vector is in the opposite direction of the gradient vector. And third and the last conclusion that we can get from this formula of direction vector is that if u is orthogonal to the gradient vector, which means that the angle between them is equal to pi over 2, then the directional derivative is equal to 0. Now let's see an application of properties of directional derivatives that we have just seen. Here we are given a 2 variable function, x times e to the power xy. Then we want to find 3 things. First, the directions in which the rate of change of f is maximum, and we want to also find the maximum value. Second, we'd like to find the directions in which the rate of change in f is minimum, and we will like to find that minimum value. And lastly, we'd like to find the directions in which the rate of change is equal to 0. So let me first remind you that by rate of change, we mean the directional derivative of f. So rate of change of f is directional derivative of f. So we are going to find the directional derivative of f first, and we are interested with this directional derivative at the point 1, 1, and it is equal to the gradient vector of f at the point 1, 1 dot product the unit vector. Now, the question wants us to find this unit vector so that this directional derivative gets its maximum value, its minimum value, and becomes equal to 0. So let's start with finding the gradient vector at the point 1, 1. So partial derivative with respect to x is e to the power xy plus xy e to the power xy. Evaluated at the point 1, 1, we find e plus e, which is 2e. Partial derivative with respect to y is x squared e to the power xy. Evaluated at the point, we find e. So the gradient vector of f at the point 1, 1 is 2e e. Okay, so now we can start answering the first part of the question. We'd like to find the vector u so that this directional derivative gets its maximum value. Now, in the properties, we have seen that directional derivative gets its maximum value when u is the unit vector in the direction of the gradient vector. So, to be able to find this, all we have to find is the magnitude of this gradient vector. So, let me do it up here. So, it's the root of 4e squared plus e squared, which is root 5e. So then if we come back to our unit vector u, so we will have 1 over root 5 times e of the unit, the gradient vector, 2e e, and this simplifies to 1 over root 5 times the vector e to 1. So for this unit vector, our directional derivative is going to get its maximum value. Second part of the question wants us, okay, before the second part, we also need to find that maximum value. So the maximum value of this directional derivative is the magnitude of the gradient vector, which we have just found it to be root 5 times e. Okay, so next we look at the minimum value of the directional derivative at 1, 1. So it gets its minimum value when the directional vector is in the opposite direction to the gradient vector. So this means when u is equal to, all I have to do is put a minus sign in front of the direction vector found in the first part of the question. So it will be negative 1 over root 5 of 2, 1. Now, the minimum value this directional derivative is going to be negative magnitude of the gradient vector, so which is negative root 5 times e. Now, the last part, we'd like to find the directions in which the rate of change is 0. So let's say that u is the unit vector. So be a unit vector, and we'd like to find a and b so that this directional derivative is equal to 0. Now, if I write the formula for the directional derivative, I would like to find the following. So we know that our gradient vector has components 2e and e. Our unit vector has components a and b, and we want this dot product to be equal to 0. So from this, we have 2ea plus eb is equal to 0. Now, I can factor out the e and then cancel it. So we end up with 2a plus b equals 0. Now, I need to find the values of a and b. So I have just one equation satisfied by an a and b. I need one more equation, and I will get that equation from the fact that u is a unit vector. So, which means that the magnitude of u is 1, so a squared plus b squared is equal to 1. Now, if I, using these two equations, we are going to find the a and b. So I can say that b here it's negative 2a, and I substituted this magnitude equation. So a squared plus negative 2a squared is equal to 1, which gives us that 5a squared is equal to 1. And from this, we find that a is equal to either positive 1 over root 5 or negative 1 over root 5. And from that, we are going to find that b is negative 2 times that, so it's plus or minus 2 over root 5. So our unit vector, when the directional derivative is equal to 0, can be when a is 1 over root 5, then b will be negative 2 over root 5, or when a is equal to negative 1 over root 5, then b will be 2 over root 5. So those are the two directions in which the directional derivative is going to be equal to 0.